Welcome back for episode 4 of Geology 113, Earth, the Instruction Manual, Adventures in Geology. This is the one that I do on oceans. Now, this is a relatively new presentation, but if you were to drain off all the water in the oceans, you would see that much of the tectonic boundaries are actually, most of them are actually in the oceans. So what you get on the continents, in fact, are the results of the interactions at plate boundaries, like mountains, rift valleys, things like that. But most of the actual activity is on the sea floor. And so we're going to talk a little bit about what the oceans are and then about the seafloor as well. We're not going to get in too much detail, but anyway, it's going to be hopefully an interesting presentation for you and a new one for me. So anyway, this is episode 4. Welcome to the oceans here. Oh, by the way, that photograph right there is from the Tasman Sea. Okay, so when we visited New Zealand, my wife and I this last year here, that was the area where you could actually look out across. If you could look far enough, you would see Australia, but probably not in that direction. We're looking at actually south towards Antarctica there, and you're quite a ways from Antarctica here. You're quite a ways from Australia as well, so you probably wouldn't be able to see it across there. Probably several. I think it's about 1,500 miles or so anyway. Maybe farther than that. I think 2,000 miles or something. Anyway, that's the Tasman Sea right there. That's the one that Abel Tasman found in his circumnavigation of the globe. What we look at when we look at Earth from space is a blue marble. At least that's what NASA calls it when they took photographs of it. They've stitched photographs all across the world, okay, together to be able to, and then some of them are actually distant like this, so it's far beyond what you would see from a normal satellite. This is, I don't know, this could have been from a space mission, I think, but it wasn't actually the space shuttle because the space shuttle is relatively close to the Earth where it orbits. It's only a few hundred, maybe 120 miles up in the sky, right? So it's not that far up there, but most geosynchronous orbits for satellites are a little bit above that. And then when you're a departing spacecraft, so like the Voyager and a few of the other ones like Viking and a few of the that we've sent into, to Saturn and to Jupiter and then on out into away from the solar system, we have one that's actually making its way out of the solar system right now. So this is the blue Earth anyway. So this is the blue marble, and it's really a water world that we live on. So 71% of the Earth, I think it's like 70.8%, but who's counting, right? So it's close enough to 71, but most people say it's 70% water that covers the Earth. And so the water is actually the natural habitat for most things on this planet. And that's where life actually thrived first. And it thrives today also on the continents, but that's almost a fluke, and it took a long time for that to happen. So anyway, so this brings up a funny idea, actually, and it's a geophysicist sort of predicament when you talk about this, but there's two ways to view yourself, right? And one of them is if you're actually, let's say you're in a river, right? And you're floating down this river in a canoe or a kayak, and you're floating down the river, and the view that you get is from that boat, and you're looking over at the shoreline, right? Well, that's an entirely different view than if you were on the shore looking at a boat on the river going past you and drifting on by with the current. And so the idea is that if you're in an Eulerian view here, you're looking from a distance and looking back onto something. It's just a different kind of frame, isn't it? It's a different perspective. Lagrangian is where you're actually in it and in the water and viewing it. And so those are just two different ways to view different things, right? So for this perspective, in fact, we're looking at an Eulerian perspective here. And if you're Lagrangian, you'd be in the middle of the water, right? If you're actually in the ocean. 71 times out of 100, you'd be in the ocean. So we have 5 oceans, and the Pacific is obviously the largest. It's also the deepest because we have the deepest trench in the Pacific Ocean as well. The Atlantic Ocean is relatively young by comparison, only a couple 100 million years ago. They're about the same actually as I think about it. So, but the oldest ocean crust in the Pacific is about 194 million years old. But so the Pacific and the Atlantic, Well, the Atlantic is what separates the New World from the Old World. We're talking about Asia, Europe, Africa, and people hadn't discovered Australia at that time. Well, modern people hadn't discovered Australia at that time. But then the New World was, discovered about 20,000 years ago, and so that is North America and South America. And so among the oceans, right? So the Pacific and the Atlantic are on either side of the New World. And then the Southern Ocean separates all of the continents from Antarctica. That's the one that circles around the globe at the bottom of the world. And then also we have the Arctic Ocean, which is at the top of the world. And people didn't really understand it until we had an opportunity to get up there in ice-free settings at times, in summer times, things like that. We've actually surfaced at the North Pole with a submarine at one point. And then, so some of the things that oceans do for us, and they're one of the most important things that they do on this planet, they actually regulate the climates. And so because we have our continents so spread apart, the ocean has a huge influence on our weather patterns and on climate in general. And then it's also a life support system for everything on this planet. And so it is food and economy that we use it for. We use it for transportation to get goods from one place to another. And it's also a source of biodiversity on this planet. So we have to take care of this planet, right? So that's part of sustainability, is to try to leave a small footprint when we are on this planet for the short period of time that we're here. So the oceans are salty. We can't drink them, right? If you drink salt water, you're going to kill yourself probably, because there's too much sodium and other ions in it. And what it does, it causes your cells to swell up, right? And you no longer can function. Your brain will swell, things like that. And so the osmotic pressure in your body just can't do it. Other animals are, adapted to deal with it, but we're not. And so, but there are places around the world that are saltier than other places. So that's what the map on the left-hand side here shows you. The Atlantic is relatively salty. The South Atlantic also has a plume of salt water close to South America there. There's a lot of evaporation in that area. And many of the world's weather patterns begin in the Atlantic there. So if you think about hurricanes and things like that. What I find here is startling, in fact, if you look at the Mediterranean Sea, which is in between Europe and Africa there. It's just enormously salty, right, because of all the evaporation and the arid temperatures that are, the arid climates that are in North Africa. And, it's not exactly a humid temperate climate over much of the Mediterranean. So it's a Mediterranean climate, right? And so you get a lot of evaporation. So that increases the saltiness or the salinity of the oceans. And you can also see on here, close to Saudi Arabia there's and that's close to that hotspot, the triple junction that's a hotspot near Djibouti in that area in the Red Sea. And so very salty sort of settings because of the evaporation. Well, where's the water go? Well, it goes into the global weather patterns, and you get more rain in places like the tropics then. So you get the rainforests, and so the rainforests are in sub-Saharan Africa and then also in the Amazon there. So we have this sort of salinity. Well, if that's the case, where's the salt come from is the big question, right? Well, the salt comes from the weathering of rocks. And so the weathering of rocks doesn't take place in the ocean so much as it takes place on the continents where it's exposed to rainwater and things like that. Well, rainwater is not salty. Well, most of it's not anyway. And so when rain falls out of the skies, it hits bedrock, it hits soils and things like that. And what you get is you have a whole bunch of materials, either in solution or as particles that are carried out to the oceans by separate sedimentary packages, essentially, that come out and deliver all these ions out into the ocean. So the oceans get saltier and saltier because of the contributions of the rivers around the world. So those rivers around the world actually give us the salinity in the oceans. Well, if that's the case, and if the Earth is 4.5 billion years old, why is it that we haven't gotten saltier and saltier and saltier through time? And in fact, that's what you would expect to find. But in fact, there is a mitigating and a control system within the ocean floor itself, within the seafloor. You actually get some scrubbing of the salts out of that. And so if ever you've seen video from the deep sea, you will notice that it actually has like black plumes of smoke almost. Well, it's not smoke, it's particulate matter that's being expelled into the water. They call them black smokers and white smokers. And then you get all sorts of scrubbing of the salts out of the ocean, out of ocean water, through the deep sea vents and places like that. Very commonly, actually, at spreading centers. So spreading centers are one of the ways that you can scrub salt out of the oceans. And so this shows you the scale for where is the least saline and to where it's the most saline. And so it goes from 31 to 39 there. A good number to remember is 34.5, and that's the average salinity of the oceans all around the world. So 34.5 parts per thousand, actually, so parts per thousand. Over here on the right-hand side, you can actually, this is a diagram from Wikipedia here that shows you what fresh water is. Well, if you have 0.5 parts per thousand of salinity, it's going to be of limit. It's going to limit what you can use in agriculture, right? So we like to have fresh water. It's good for humans to drink. It's good for irrigation of crops and things like that. And so in many of the oceans where you have lower salinity, for instance, in the Black Sea here, it's only 8 parts per thousand. You still can't drink it, so you wouldn't want to drink water out of the Black Sea. I've had a former professor who would try to drink and see if he could actually taste the difference in salinity. Very carefully measured how much salt went into water and what a person can tolerate. But he wasn't able to tell, the amount of salinity when it got salty enough to be considered to be regular, normal ocean water. So anyway, in the Black Sea, the Baltic Sea is 8 parts per thousand. The Black Sea is actually 18 parts per thousand. Here's your average, 34.7, 34.5 roughly. So it's brackish water if you don't have if you have less than what is normal salinity. It's considered to be brackish. And then saline goes all the way up to 50 parts per thousand. And so you get briny waters beyond that. And so there's actually some freshwater lakes that are actually kind of briny. For instance, Great Salt Lake in Utah is one of those places that's very highly saline, in fact. And so the salt comes from rivers feeding into oceans or bodies of water, and it gets scrubbed out by ocean processes in a chemical sort of fashion in the seafloor. So if we take Earth's water, that's about 98.5% is our salt water in the oceans. It leaves very little behind, and so 96.5 it says in this diagram here. There are other saline lakes and things like that. That's a little less than 1% there, and then 2.5% is fresh water. But the trouble is, okay, that's 2.5 for people to use for irrigation. It's 2.5 for people to be able to drink, right? And so when you zoom in on this, right, so like most of that's actually in glaciers, as it turns out. I mean, we talked about 3 miles of ice in Antarctica, so that's a lot of water, but it's all locked up in ice and you can't use it. The same thing with Greenland, right? So it's mostly fresh water that's locked up there. And then there's some in groundwater as well. Well, we can use groundwater, but it's not the most efficient way to get water. Most of the water that we like to get is actually clean surface water. So that's going to be in freshwater lakes and freshwater rivers. And so that's only 1.2%. And I teach in Missouri State University, which is in Springfield, Missouri, and we get a lot of our fresh water from a couple of lakes, actually. So we get it from Fellows Lake, which is on the north side of Springfield, and then that is funneled into McDaniel Lake, which is specifically designed to be a freshwater reservoir for use in freshwater usage within the city of Springfield. And then, so those are two sources. And then we also pump water. About 2/3 of our water comes out of the James River, which flows up from around Marshfield down past Springfield. And it's pumped out of the James River and into the Blackman Water Treatment Plant, which is on the east side of Springfield. And that supplies the water towers around the city. So that is our source of water. They treat the water to try to get rid of the bugs and the particulate matter and things like that out of it. So they let it settle and they they flocculate it with polymers and things like that to get the algae out, and then lastly they filter it through sand, and they used to filter it through garnet and a whole bunch of other things, but that was too expensive to do apparently. And then they run it through some charcoal as well. Commonly they run it through charcoal. I'm not sure they do that all times of the year, but in the summertime when it's particularly warm, they like to get the flavor to where it's palatable. So of all of that fresh water that we have at the surface, about 21% is in lakes. A lot of it is still in places we can't use, like in ground, in ice, okay, permafrost it's called. So the ground ice and the permafrost account for almost 1% there. But then we also have the rivers, and there's soil moisture, and then there's some in swamps and marshes that you wouldn't want to drink because of all the things in it. And then the atmosphere actually accounts for like 3% of the world's fresh water. So having said that, what's the one commodity you really don't want to have to pay for? I regard it as a human right. It is fresh water. As a human being, you deserve to have fresh water, in my opinion. And but there are those out there, and I won't mention any name, but the world's richest man right now says, "Oh, it's so cheap to be able to get desalinated water." Well, I looked it up, okay, and so the price for desalinating water is about $5 per 1,000 gallons. Now, if you have desalinization plants around the world, now that is a way to survive, okay, I grant you that, but the fact is you don't want to pollute the fresh water that you already have. And we can't allow corporations to pollute that fresh water either. And so we need to be very careful and sustainable in our habits. And so that is one of the things that we need to learn. They do use desalinization in several places around the world already. So United Arab Emirates do that. Saudi Arabia does it. Kuwait does it. These are all areas that are very arid. They have deserts in them, right? So Oman, Qatar, Bahrain, Morocco has it because it's a desert, it's connected to the Sahara, right? And then India, because India is quite arid because you only get water a few times of the year there during the monsoons and so forth, right? China has some desalinization plants as well because they have such a huge population that they have to serve. And then also Singapore, it's the same thing. It's such a small country with such a small footprint for its municipality. So in the country that is that municipality. And then Australia too, because it's an arid place as well. And Spain, because Spain is pretty much semi-arid across much of it. And then lastly, even in the United States, there are desalinization plants, even in Florida and in California. So it behooves us to be able to protect our freshwater resources. It's the most important thing we can do. So it's important to get out and clean up streams and to prevent pollution from ever reaching those streams. And if it's bad enough to have like groundwater pollution, it's really even worse to have freshwater pollution into rivers and lakes. So, okay, I'll get off my soapbox here now. We're going to go on into the oceans now. So we're going to take the deep dive in the oceans now. I found this website just recently here, and it is superb. Now, this is from NOAA. NOAA is this is their National Center for Environmental Information, but NOAA is the National Oceanic and Atmospheric Administration, right? And so they provide this evidence based on the data that they've collected from cruises across the world. And so on here, you can actually see track lines and things like that on this diagram. If you go to the menu, which is on the left-hand side there, and click off the multi-beam data sets. Now, if you want to get into those, you can do that, but then also click off the hydrographic survey online thing there. And then what you want to do is get all the way down to where it says digital elevation models. So that's like the fourth gray banner across here. Click on that, and you want to get the DEM color shaded relief. And when you do that, you wind up with images like this of Northern California. It puts the state boundaries on there because NOAA is actually a governmental agency and they want to show you where America is relative to everything else. But they show you these high resolution seafloor maps as well as the land-based DEMs, the digital elevation models for land as well, on here. And you guys already know this. You know about the Juan de Fuca plate. You know about the Pacific plate. And you know that there's a spreading center between them. That spreading center is represented on this diagram by that little line that runs up. You see where I have it labeled Pacific plate there, and then the Juan de Fuca plate a little higher there. Well, that's a little sliver of the Juan de Fuca plate to the right of that line that crosses this in between Oregon and California there, and that ridge that runs through there. So that ridge is I can't quite make out the writing on it right here, but you can see that the Pacific plate jumps over then and is actually part of the part that's off the coast of California, Central California and Southern California. That's actually considered part of Northern California there still. But that is the Cape Mendocino triple junction right there. That is where the North American plate is overriding both the Juan de Fuca plate and the Pacific plate. So three plates come together at that point at Cape Mendocino. And if you've never been there, and many of you probably haven't, I'm guessing, it's one of the most beautiful places on earth. If you can find a place that will give you a job there, move there, okay? It's really a neat area right there. I love Northern California, spectacular. So anyway, this is a triple junction here, and that is a fracture zone that runs through the Pacific plate there. And so, but it's the thing that fracture zone actually, it's the Mendocino fracture zone that separates the Juan de Fuca plate in the north from the Pacific plate in the south, and the ridge separates the Juan de Fuca plate in the east from the Pacific plate in the west there. So it's a spreading center right there and a triple junction. So that's a triple junction right here within the waters that are part of the exclusive economic zone of the United States, which runs out 200 miles out into the oceans. And so those are things that we reserve for our own uses. Now, this is really kind of cool for two things here. You can see where that fracture zone is in the ocean there. If you trace that on land, you'll come up to where the first volcano is. So you have to subduct a plate for a certain distance before you actually get a melt, and then you get volcanoes that develop there. So Lassen Peak is the southernmost of the Cascade Range. That's Lassen Peak over here in Northern California. And then you get the Cascade Range running all the way from Northern California. Mount Shasta is below some of the labeling I have there for Cape Mendocino. But Mount Shasta all the way up and up to southern part of British Columbia there where Mount Garibaldi is. And so that's the Cascade Range. It's all volcanic in origin. And the range that's outside of that, so you can see that big broad valley that's in western Oregon there. That's another nice place to live, but that's called the Willamette Valley right there. So the Willamette River runs through that area. And then separating Oregon in the north from Washington, the state just above it there, is the Columbia River there. And so that mountain range that runs between the Willamette Valley, that sort of green area that extends in southward into Oregon there, and in between it and the ocean, that's the Coast Range in there. And so the Coast Range there is a lot like the Coast Range in California. And so it's all accreted material. It is an accretionary prism of material, in fact, from our plate tectonic sort of like understanding. So you get accretionary prism, you get a valley, kind of like the Central Valley in California, and then you get volcanoes. Well, those volcanoes used to be in California as well 17 million years ago, and in fact, they left behind the Sierra Nevadas, which today are mostly granites, where those mountains have been uplifted and it's eroded everything off the top of those plutons that are down there. We're going to talk about plutons when we venture into igneous rocks, okay? So beyond that, in fact, you get into something called the basin and range. And so the basin and range are where you see all of those linear mountain ranges in there. That whole land has been pulled apart. So as soon as you stop the subduction in the West Coast, all of that area just decided to like relax. And when it relaxed, it sort of split apart here. And remember, you're also overriding the top of a spreading center, right? Well, the spreading center is no longer active when it's below a continent, but it still was able to pull the continent apart there. At least that's the understanding I have of it anyway. And so it's actually been extended up to 300% when you get into the basin and range. And that's the area that's in Nevada there that extends just barely into Oregon and then on into Idaho as well there. And that's the Rocky Mountains when you get over into Idaho, or above the Snake River Valley there. So that is kind of a cool setting. And so for landscapes, it's just amazing. When you look at landscapes, you can interpret what kind of geologic history they've had through time here. And so we're next going to go to things that are more relevant in the news these days. And so if you didn't know about it already, in August there was a huge earthquake in the Kamchatka Peninsula. That's that little piece of land that sticks out below Russia, the eastern part of Russia here. You can see where the asterisk is here, that red asterisk there. That was the location of that earthquake. It was an 8.8 magnitude earthquake. It's one of the larger ones we've had in the last 100 years anyway. So as earthquakes go, the largest we've experienced in modern times is about a 9.6. I think the Tohoku earthquake in Japan was about an 8.6 or 8.8 also. But this was an 8.8 here. And the interesting thing is you can see a trench off the shore there, right? So we're going to zoom in on that. And so, okay, before we do that, I want to point out a couple more things here. When that earthquake went off, there was a volcano that almost erupted almost immediately after that earthquake. And so that's what you see in the top photo up in the upper left here. And so that earthquake went off. And then 6 other volcanoes, the earthquake went off. And then you had that volcano go off. And then you also had 6 more volcanoes go off almost immediately afterwards. And so all of those things are probably related to the subduction and the shaking, essentially, of the earthquake, that seismic event. So if that's not enough, okay, so if you want to look for a place that's particularly dangerous to live on this planet, it would be along these ocean trenches. Those are the Aleutian Islands. They're very desolate. When you get out into the Aleutians here, you can actually see, and the westernmost is Kiska and Attu out here. And so there's a subduction zone right in front of the Aleutian Islands and the Alaska Peninsula, which is the bit that sticks down off of Alaska there when you get closer into the main part of Alaska. So Anchorage is up that inlet there. That's Cook Inlet that you see just north of Kodiak Island. So the Kodiak bear is probably the largest on Earth for grizzly bears anyway, up to 1,700 pounds or so. So that's not a place you want to hang out either, probably. But that area in there around Cook Inlet has been used for, well, lots of things. During World War II, my father was stationed there and helped build Elmendorf Field. He also got transferred then to Nome, Alaska, which is up on that little peninsula that sticks out in the middle of Alaska to the west there. And so he was in Nome, which is on the south side of that peninsula. And I actually got to visit a place called Kotzebue, which is up just north of that on in that embayment that's the second of those embayments, the one that's a little bit farther to the north. I was working in an area of the western end of the Brooks Range. That's the mountain range that runs across the northern part of Alaska there. And north of the Brooks Range there, that's actually called the North Slope. And so the North Slope is where there's, two of the major, many of the major oil fields in North America, in fact, are in that setting. So in Arctic sort of like terrains there. Also, the highest mountain in North America is in this area too, 20,000 feet, right? So it's over 20,000 feet, Mount McKinley there. President Trump just recently changed the name back to Mount McKinley to honor that former president who was assassinated. Denali was the Native American name for that mountain. So Denali was the high spot in what they call the Alaska Range. So that's the Alaska Range across southern Alaska there. So we're going to go look at this trench next. And so here's the location for that 8.8 earthquake. You can see it in the sort of gray circle there that shows you the extent of where most of the origin was for that sort of earthquake. They're showing you the magnitude of that earthquake by the diameter of that circle. Now, the circle in the upper right on the left-hand side of that image, that just shows you the 3 plates there and the location where this INSAT map was taken here. And so you can see where the trench is down here. It was below the North American plate. So Kamchatka is actually on the North American plate there. And so the Pacific Ocean is being subducted and the North American plate is overriding it to the east there. And so because these things have a tendency to stick, I don't know. Maybe you've been like at a table at some point where you've had maybe sweaty hands, and you put your hand on the table and lean on it, and next thing you know is like, well, the friction keeps you in place until it doesn't, until you slip. And so they call that stick slip. And the same thing happens with plates. And so the North American plate all of a sudden had a catastrophic failure and it slipped. And when that occurs, you get a seismic event. And this one happened to be pretty large at 8.8. It was pretty close to 9. There was the earthquake in Banda Aceh that generated the 2004 tsunami at Christmas time. That was about a 9, I think. So that's the only larger earthquake we've had since. So 7 Earths, this earthquake probably first of all, it generated the eruption of what they think are about 7 different volcanic eruptions after that. But then you got a whole bunch of these extra earthquakes after that event. And so these things are actually called aftershocks. And so the aftershocks, many of them were relatively shallow here. At the bottom of the diagram here, you actually see a cross-section where the Pacific plate is being overridden by that North American plate there. And you can see the locations and how deep many of those aftershocks were. Well, they weren't as deep as what the 8.8 is, which is in that gray circle there. So the 8.8 was about 20 kilometers deep, and it generated all of these extra aftershocks. And so the ones that are in pink there are farther, they would be on the Pacific plate. Their focus is what that's called, actually. The focus is actually located on both plates. And so both plates would have faults that would be going off after the main event there. They have not witnessed anything like this for 300 years. So 300 years it's been since they've had a whole series of earthquakes in this area. Yeah, there were settlers there back 300 years ago, even in eastern Russia here. So, okay, we're going to go on from that. So that is kind of cool. So plate tectonics describes what we see in the oceans. And so the oceans are where most of that activity actually occurs. And so here you can see the deepest point in the oceans right here. That's the Challenger Deep. And so that's 36,070 feet there. And you can do that with bathymetry, right? So you can get the bathymetry with really seismic events, so you can actually get the bathymetry with sonar, and you can also do it with multi-beam, right? And so they've gone through and mapped all of that area previously, but one of the things that we had never done up until the 2000s, right? So it was actually in 2012, and you're going to like this actually, but I'll get to that in a minute. First of all, let me tell you this, like what you're seeing here is a trench. That's the Marianas Trench right through there, and the Challenger Deep is the lowest spot in the Marianas Trench. Now, it's not where you might expect it to find it, right? You might expect it to find it east of the Marianas Islands there. That's Guam at the very bottom down there, so that's one of the Marianas there. But in the Challenger Deep there, it's pretty deep, right? So all of ocean crust, as you've also been told already, is made out of basalt. And the ocean crust is relatively thin, somewhere around 10 kilometers thick, usually, compared to the continents, which are much thicker, about 70 kilometers or more. But not all basalts are the same. They all get generated out of the mantle, but they're not all the same. And so let me explain these things. These things are called island arcs when you see a whole series of islands like this. And island arcs also describe Japan. Okay, so we'll talk about that in just a minute here. But island arc basalts are abbreviated IAB. Island arc basalts have a different chemistry than other basalts. They may look the same, but they have a different chemistry. And so when we look at ancient basalts, we can tell if they were in an island arc or whether they were in a mid-ocean ridge or whether they may have been associated with some sort of hotspot. And so the mid-ocean ridge basalts are called morbs. And so the IABs or EABs are called IAB. That's the island arc basalts. They would be associated with subduction. Mid-ocean ridge basalts are depleted mantle that actually forms them, and they form very shallow just below the mid-ocean ridges. Well, you can see that this is a trench. There's subduction going on there. It's not spreading there. And so that is but seafloor Seafloor also records the morbs, right? So the morbs are the mid-ocean ridge basalts. And then lastly, when you have hotspots, those things are going to be called eorbs or oibs. Ocean island basalts. And so those tend to be evolved from things that are very deep in the mantle. People call them mantle plumes. Remember, we talked about where do slabs go when they get subducted? They can go all the way to the core mantle boundary, get melted again, and then come right back up as plumes. And those plumes, in fact, give us oibs. And so that's kind of a neat aspect of basalts there. So 3 different kinds of basalts. If there's some place that's the highest, the lowest, or the farthest away, people went to the moon in order to say that we've been there, but also to study it. They brought back samples and things like that. James Cameron, that guy from the Titanic, from the Avatar franchise, right? So we just have the release of the newest Avatar movie this over Christmas time here, set box office records and everything like. This guy is incredibly talented, and he is an adventurer. And so as an adventurer, he took upon himself to say, let's build a machine that's going to take me down to the deepest of the oceans. And he went down 35,787 feet in that vehicle that's on the lower right here. And so that, it was called the Deep Sea Challenger here. And James Cameron went into it and lasted down there for 3 hours, came back up then, right? So they wanted to design a vessel that would take them to the deepest spot in the ocean. It's very similar to what they call a bathysphere. And so bathyspheres are actually round and spherical in shape, and they have a little window, essentially, that allows you to look out, and then lots of lights to light up the landscape that's around, or the seascape that's around you there. And so this thing actually had ballast tanks above it and lots of electronics and things like that. Now compare that with the Titanic expedition that went out recently here, which such a catastrophe. I don't want to talk about it, in fact, but it was kind of a fiasco, because whenever you design something, you don't make it out of a cylinder, you make it out of a sphere, because sphere can actually push back against the pressure much easier. Anyway, he went down there in March of 2012, believe that or not. It's like, I don't know that I was paying attention at the time to that. I should have been paying attention, because that's really quite a feat. So the Challenger Deep is deeper than Mount Everest is high. Okay, let me put it that way. So that's what the diagram on the left here shows you, right? So if the Titanic was at 12,400 feet in the oceans, not in the Challenger Deep, by the way, that was in the Atlantic, but it was relatively deep. He sent an ROV down there to look at the Titanic, and then he got the idea. It was like, why don't we just go in a manned vision, a version of that to the deepest spot in the oceans. And so they went down there first with unmanned rovers, right? So these remotely operated vehicles, an ROV. And so they went down there to be able to examine the seafloor and things like that. That's happened many times around the world. But in fact, to have a manned version of that is really pretty spectacular. So over here on the far left-hand side, you can see the mountains, right? And so there's the Burj Khalifa for the estimate of the highest thing that humans have ever built there. The city of Denver is a mile-high city, right? So it's 5,280 feet. That's how many feet are in a mile. And that's kind of the average for what the height of Denver is below the Rocky Mountains, by the way. So the Rocky Mountains rise above it there. And then you get the Matterhorn. The Matterhorn's 14,690. And then Mount Everest is over 29,000 feet high. Really quite an adventure that James Cameron had here as, not as the director. What an incredibly talented guy here. So we're going to go on around the world now. So we're going to take a look at a few more structures around the world. One of them is Krakatoa. Now you may or may not have heard of Krakatoa. Krakatoa was a huge volcano that erupted in 1883. And it was the volcanic eruption heard around the world. Yes, it made so much noise that the reverberations from that eruption could be heard all the way around the world. It was like ringing a bell. And so that is where Krakatoa is today. And in fact, Krakatoa itself blew up. And today there's a volcano in the middle of that, which erupted just recently here. It was about 800 feet high and then blew part of its top off again here. But That volcano is in between the islands of Sumatra in the north and Java, which is off to the east here. And so that eruption occurred in 1883. You could hear it around the world. When it blew up, it generated a tidal wave, and that tidal wave it killed 30,000 people in the city of Batavia. Now, that's the old Dutch name for the Indonesian city of Jakarta. But Java used to be a colonial possession of the Dutch, and so they taken this area to harvest not only the rubber trees, but also coconuts and spices and things like that. But, Indonesia gained its independence in the 1960s, I think, or maybe 1960. And Batavia, they changed the name back to the original spelling, which was Jakarta. And so that's the location for Krakatoa there. Anak Krakatoa is the remains of that in the middle of this island cluster that's in the middle where that volcano was there. And so you would think that would be made out of basalt, but it is not. Okay, so that volcano, in fact, is a mixture from the continental crust, which underlies Sumatra and Java, part of its continental in source there. And it's a rock called rhyodacite, Rhyodacite, rhyodacite. So it's a mixture of the two. It's part basalt, and then it's part felsic material from the continental crust there. But it was generated because of that trench that's down here. So that is the Sunda Trench that you see down here. And that's the Sunda Plate up here that Java and Sumatra sit upon. So that is, and the Sunda Shelf is behind it there, that relatively shallow water behind it there. Now, I didn't explain this before, but the dark blue on here is deep water. The light blue is shallow water here. And so that extension of the Sunda Shelf there that comes out in between Sumatra and Java blew up as a volcano from the mixture of lavas that were generated from subduction. And if you'll notice, there's two different directions. Sumatra kind of heads off to the northwest there, and Java heads to the east here. So there's a bend in that plate boundary there between the Indian Ocean out here that's being subducted and the Sunda Plate there, the Sunda Shelf. And so that's Krakatoa there, 310 decibels when it went off. Some people say that, decibels is a fair way to actually record the eruption of that volcano, because decibels measure something a little bit slightly different from that, but it was the equivalent of 310 decibels. Next, we're going to go to Hawaii here. And Hawaii's really nice, actually, I gotta say. Here's a guy that's running away from a lava eruption. He's just collected some lava in that little bucket that he has here. He has heat-resistant gloves and a face mask that's actually heat-resistant as well. I'm sure he has other heat-resistant underwear underneath of that T-shirt that he's wearing for the USGS right there, trying to advertise for the USGS. In Hawaii, they have something called the Hawaii Volcanic Observatory. I've visited there before. It's really quite an amazing sort of place. It overlooks a sort of volcanic crater called Halemaumau. Kilauea caldera first. And so Kilauea caldera, it sits right on the shoulder of Kilauea caldera. And then Halemaumau is the second caldera within a caldera there. And so that is continually erupting, and it's been continuously erupting in this area since the 1980s. Okay, so I think maybe there was a tiny break, but it didn't last for more than a year. So in 1984, 1983, I think the volcano began to erupt, and it's been going off continuously. This is a lot of, it's what we would say is an effusive volcano. It puts out a lot of material. And so the Big Island of Hawaii is the biggest of all of them. And the main chain actually is in the shallower water here. And then beyond that, you can see some of the light blue that's out along the Hawaiian chain there. And that includes things like Midway is out that way. Kure is the farthest east, farthest towards the east. I call it the east. It's the farthest west of these islands. So Kure, Kure, is out that way. So that is the Hawaiian chain right there, and it's caused by a hotspot. It's right in the middle of the Pacific Plate. So the hotspot is sitting below that at some depth. And what happens is that plume that generates that hotspot comes upward like a flame underneath of a tin plate, if you will, and heats up that spot, melts the rock there, and then you get volcanoes. And so there's a lot of lava that's pooled up below the Hawaiian Islands there. And that's been going on for over 80 million years. So that hotspot, we think, is relatively stationary. And so there's actually a twin track of these things where it seems like the hotspot will erupt in two different lines of volcanoes through time. And that goes all the way back, at least to Kauai anyway. So Kauai is just beyond, a little bit to the west of Oahu there. So this is the Hawaiian Island chain. And if you trace it, you can see where there's a bend that makes a bend right there. That happened about 43 million years ago. There was a change in the trajectory of the Pacific plate. And that island, it's not really an island chain beyond that. It's seamounts, actually. And so even some of the things between the main islands and Kure and that bend right there, those things are called seamounts. They're below the ocean surface. And so the seamounts that extend farther out, they're called the emperor seamounts. And so the emperor seamounts go all the way up and then are subducted below either Kamchatka or the Aleutian Islands there in the Aleutian Trench, or that Kuril Kamchatka Trench that's listed on this slide here. And so the trajectory of the Hawaiian Islands have changed through time. So here is the location of the main islands right here. There's actually 7 of them, I think. Yeah, so it's the Big Island, Maui, Kahulave is a smaller one, Lanai, Molokai, Oahu, and then you get Kauai, and actually Kahulave. I think I mentioned Kahulave. Niihau is the other one. So Niihau is reserved for indigenous Hawaiian peoples, and they live out on the western edge of the main islands there. So those things right there, those islands right there, they're over the Molokai fault zone there, you can see. And so you can see the Cape Mendocino fault zone out there. It stretches all the way to the Emperor Seamounts there, in fact, right? So you can trace these things backwards. And this actually gives you the ages. And so the last age that's listed on here is 75.8. But I think when you get back to the very back there, it's about 85 million years old. So the bend happened about 43 million years ago. That was during a time period called the Oligocene here. And so the Pacific plate was moving to the northwest, and then today it's moving to the west-northwest. So it's a more westward sort of direction for the Pacific plate, running over the top of that hotspot. And so down here I can show you the trajectories on these things. So the hotspot itself has changed trajectory. That's in the red there. Actually, the plate motion is changed over the top of the hotspot. So the apparent hotspot migration seems to go to the southeast and then to the east-southeast there, whereas the true thing that's actually generating the island chain plus the seamounts here, it goes to the west first and then it goes to the northwest. Here's the islands themselves, and this shows you just some of the volcanic eruptions there. That's in the Kilauea caldera here. You see over on the top view there. And there's a fountain eruption then going on. You can see that people are not too concerned about this, right? And so here you see folks watching that fountain erupt right there. But then sometimes in the eastern rift zone on the Big Island here, to the east of Kilauea, it'll erupt into neighborhoods. And so some of the neighborhoods, which have paved roads, obviously, here you can see a flow coming down the road here. That's a very viscous flow there that's actually, seldom do you, I won't say never, because people have been killed by the eruptions in Hawaii before, but not too many people have been killed, let me put it that way, unless they were sacrificed, I suppose. So the volcanic eruptions are one of the hazards that you deal with in this part of Hawaii here. And so, but you also get earthquakes. And so people are concerned about the earthquakes in Hawaii in particular. In the map over here on the right-hand side, you can actually see where the active flows have been over the last 100 years or so here. So that is Mauna Loa, the mountain that has the 2 large flows that come out from it. One of them heads down towards Hilo to the northeast there. The other one heads down to the southwest there toward the Kona coast there. And then Kilauea is actually on the south of Mauna Loa here. And so that's this area that is blanketed with red down here. That's called the Pali down there. And so the Pali actually had a lot of volcanic eruptions in it. And so the lavas will go over this cliff essentially. Quite spectacular sort of setting there. So Kilauea itself is actually that little isolated red dot. It's the beginning of that area to the south and east of Mauna Loa there. Some of the historic flows have gone all the way up to Lahaina, which is on the west coast. That's that western point of the big island of Hawaii here. So that's dangerous enough. Okay, you can usually get out of the way of most of the lavas here. Some of them are fairly non-viscous and can flow pretty rapidly, but the viscous flows go pretty slow, and so you can get out of the way of them. It may destroy a house, it may destroy some infrastructure, but that's, you can rebuild, you can move somewhere else if you don't want to be hit by a volcanic eruption in Hawaii anyway. For real risks in this area, earthquakes are one. Number two is the submarine landslides. And that's what this slide really shows you better than anything. Those submarine landslides are on the ocean floor here. This whole talk's about oceans, right? And so those volcanic eruptions on the islands wind up destabilizing, and sometimes gravity takes over, and then you get these huge slides that'll come off. Look at Molokai. The island of Molokai had this huge landslide that took away half of the island. It took away half of a volcano. So if you can imagine if you had Mauna Loa and then all of a sudden lost half of it into the ocean. That's what it could happen, okay? Oahu, the same thing, right? So Oahu went to the northeast there, and half of Oahu is gone there as well. And then there's one to the west there, so the west side on the west range in Oahu, it lost some material into the oceans as well. It's the same story over and over again here. Even the south side of Kauai, and the north side of Kauai, the northeast side of Kauai. Even Maui had some submarine landslides. These things are not dangerous in and of themselves because people don't live on the seafloor, but what it does, it displaces ocean water. When you displace ocean water, you generate tsunamis. And tsunamis are one of the big things that you can get. You can get them from local here, which is, with a submarine landslide, even small ones can lead to small tsunamis. There was one on the south end of the Big Island that it killed some people, it drowned some people back in the 1970s, I think it was, 78, 79, somewhere in there. It was a Boy Scout campground, in fact, and so it was a collapse of what they call a lava delta that led to a tsunami there. Another danger is if you have earthquakes like the one in Kamchatka, it can actually generate a tsunami from Kamchatka that could hit the Hawaiian Islands. And so you could have long-distance earthquakes that actually impact people in Hawaii. That's happened many times in the past. There was one in the 1940s. There was one in the 60s, early 60s, I think it was. But what happens is many of the narrow valleys in Hawaii that are caused by erosion, because the rocks are not really very resistant to erosion. So you get these beautiful valleys that develop, and they're very good grounds for like villages to be established. And so on the north end of the Big Island of Hawaii, some of those valleys in there are notoriously dangerous for tsunamis. The 1964 earthquake in Alaska actually generated tsunamis in this area. So that's Hawaii there. And so there are all sorts of risks. Okay, tsunamis from local or distant areas, and then, of course, shark attacks, right? Somebody was killed recently here just off of Maui, I think, by a shark attack. Yeah, Maui has its own issues too. What happens here weather-wise is the west side of these islands tends to turn into a desert, and the east side tends to turn into something that's a luxurious rainforest, more or less. And so if you live in these islands, there's food growing on every tree. If you're on the east side, on the west side, they grow things like coffee. And so anyway, that is the islands of Hawaii here, the Hawaiian Islands. The next one's kind of interesting. This is the Galapagos Islands. And so the Galapagos Islands, just like Hawaii, but not making a chain, was the result of a hotspot. And so the Galapagos Islands are a part of Ecuador. And so they're about 3,000 miles, I think, away from 2,000 miles away from Ecuador. But in fact, they were a whole series of volcanoes that were erupted below that ocean. Well, the ocean plate was there. You get a hot spot, you pull up magma below it, and the next thing you know is you have volcanic eruptions. And so those are the islands themselves here. You can see Isabel is the largest of the islands here, the whole string of volcanoes on it. On these islands, in fact, you find these ancient tortoises. It was always a mystery. How do you get giant tortoises out into an isolated desert island like this? And people recognize these all the way back to when the first explorers showed up here in the 1500s. They found these giant tortoises, and they were seen as something that they could eat, essentially, because they didn't really have fresh meat or any sort of fresh food to eat on these voyages. And he reported them in the 1500s. Darwin came around in the 1840s, and in the 1840s, he described many of the tortoises here. And so some of these tortoises can live to be 200, or I've heard reports that some of them could have lived until they were 300 years old. So absolutely ancient creatures living on some of these islands. And the interesting thing that Darwin found was there were different subspecies on every one of the islands. So these giant land tortoises probably came from mainland Ecuador, and they probably drifted out on logs or something like that brought them out here. And they've been around for a long time, but they haven't been around for hundreds of millions of years, I'm pretty sure. But anyway, these are the giant tortoises down here. So anyway, that's the Galapagos Islands there. Another one of these island chain. It's not a chain in this case. It's an island over a hotspot here. So not a chain like the Hawaiian Islands. So you get you get oibs in Hawaii. You get oibs here in the Galapagos as well. Okay, this is an island that originally started out as volcanic, but that was several hundred million, well, a few hundred million years ago anyway. I think the oldest rocks are Cretaceous here. And there's still actually some places that have some volcanic material in them along here, but that's in the Blue Mountains, that sort of mountainous area that's at the east end of Jamaica here. If you look at this thing in a large scale here, you can see Pedro Bank here, just south of Jamaica, right? So that would have been an island back during the last ice age, at least for part of that last ice age. And so that's Pedro Bank down here. And then Jamaica has this southern shelf on it here. That's still part of the island there. Jamaica itself is actually part of the boundary. And so the boundary runs right through the middle of Jamaica. In fact, that's called the Plantain. It's the Enriquillo Plantain Garden Fault that runs from Haiti, which is off to the east of this map, and it runs into that southeastern tip of Jamaica there. And then what it does, it kind of heads up and cuts across northern Jamaica and comes out at Montego Bay in that area, where it's called the Duanval Fault. And there's a whole series of other faults through a Shiloh Fault, and then there's also I think it's called the Walton Fault that runs through the west coast there in Westmoreland there. So anyway, that's Jamaica, and I've been to Jamaica several times, so I had to show you a map of it. I love Jamaica, and it's just a beautiful island, beautiful people, beautiful music, beautiful food, and it's like no problems, man. You know, this is Jamaica, Iriman. So this is in Jamaica. And so Jamaica, at the edge of that fall, to the north of it there, you can kind of see the Cayman Trench there, right? So the Cayman Islands are on the opposite side of that trench there. And so the Cayman Islands, that's a little deep water area. There's a spreading center in that area. So that little area in there, if we talked about plates, that's actually what's called a microplate in there. So that's the Gonave microplate. It's named for Gonave, which is in Haiti, just off to the east here. So the Gonave microplate runs through there. It's in between Jamaica and Cuba. So that is a small spreading center in the middle of a microplate there. You can see how kind of complicated it can be with plate tectonics with this. The area that Jamaica sits on right here extends all the way over to Central America, where it's part of what they call the Nicaraguan rise right here. So it goes all the way to Nicaragua, that relatively shallow water at the bottom here. It's not as shallow as Pedro Bank, but there are some banks in there. So that is Jamaica right there. It's on a plate boundary. And the plate boundary there is mostly not subduction. Most of it is actually a transform plate boundary, at least in the northwestern part there. There's a little tiny bit of subduction probably going on to the north and east of the Blue Mountains at the eastern tip of Jamaica there. So there's a little tiny bit of subduction, and that's part of they call it the Puerto Rico Trench. So it stretches all the way across northern Haiti, all the way to Puerto Rico there. So that is Jamaica. Really spectacular place. You get a chance to visit, go to Montego Bay, and if you need some content, or send me an email or something, right? And so you can get me at stratigraphics@gmail.com, but with an X, right? So stratigraphics with a Gmail address there, and I can give you information on who to call and who to visit with in order to have a wonderful vacation in places like Bluefields Bay, which is on the western shores of Jamaica here. And he'll even take you down to Treasure Beach. Spectacular place down there. So that is Jamaica. Jamaica sits astride the North American plate, or the Gonov microplate that separates North America from the Caribbean plate there. This is the Caribbean plate itself right here. Now, in the news, you've probably heard a little bit about Venezuela. So Venezuela is that southern area down here, and that's Lake Maracaibo. That's that sort of large inland sea right there, next to the Gulf of Venezuela there. And so there's a lot of oil in this area, obviously. But what I want to tell you is there's a strike slip boundary that runs across that part of the Caribbean plate there. And so there has been in the past some subduction out here. That goes all the way over to Trinidad, which is over here on the lower right-hand side. The island of Trinidad is over there. So that strike slip plate runs all the way through there and runs up around the northern edge of Venezuela here. If you go over to the east here, now this is where it gets kind of interesting. So Trinidad and Tobago, that island that's just a little bit to the north of Trinidad down here, that those are joined together, and that's actually part of I'm pretty sure it's part of the Caribbean plate there, but there's subduction going on underneath this, right? And so you can see where everything kind of peters out from the Lesser Antilles. These islands are called. The Greater Antilles are the big islands like Puerto Rico. Dominican Republic is on Hispaniola, right? And so Haiti and the Dominican Republic share that island. Puerto Rico is on it. Jamaica is one of the Greater Antilles, as well as Cuba. So those are the Greater Antilles. The Lesser Antilles are all these islands that are spread out, and that includes the Virgin Islands out here all the way down to Grenada, which is where St. George's is there. So you can see all of those islands, and they are volcanic, especially along this leading edge here. So Martinique has volcanoes. Guadalupe has volcanoes. All of those places are mostly volcanic islands that have had reefs that grow up over them and things like that. But that's all due to subduction. So the Atlantic is actually being subducted below the Caribbean plate here. And it doesn't matter what size the plates are. These things, they're still interacting with one another. And so what do you get in these sort of situations? Well, you get volcanoes and you get earthquakes. So that is the eastern edge of the Caribbean plate there. Quite a place to see. If we go out into the Atlantic Ocean then, and right in the middle of the Atlantic Ocean on some islands that belong to Portugal. In Portugal, they have the Azores, and so the Azores here have a whole series of islands. And the interesting part about the Azores is they sit astride the mid-ocean ridge there. So the Atlantic mid-ocean ridge is like, right there. And so it separates this island to the left from these islands that are over here to the right. Now, if I were to ask you what kind of basalts do you get there, there's a mid-ocean ridge right there. You would expect to find a morb there, right? These other islands, in fact, are probably related to hotspot volcanism. So there was, at first, probably a hotspot that could have generated some of the seafloor spreading at that mid-ocean ridge. And so, but eventually, the mid-ocean ridge took over. And so you get those would be oibs. And so there's a mixture of oibs and morbs in the Azores. it's really kind of fascinating. So one of my colleagues at Missouri State studies some of the lavas that are coming out of this. In fact, one of the students was in my stratigraphy class. She's working on a project with Dr. Gary Michaelfelder, who's at Missouri State University. He's the director of the School of Earth Environment and Sustainability, and so he studies these types of volcanoes. So he's big into volcanoes in South America, but also here in the middle of the Atlantic. That's a good thing. So we're going to go on to the next one here. We're going to stick with oceans still, right? And so we're looking at the southern tip of Italy there with the boot. And then you can see Sicily out there where it's being the football that's being kicked. It's not quite round, however. Sicily is actually on the African plate. So you can see Africa down here at the bottom. Tunisia is down here, and that's the ancient area of Carthage. If you were to look at the historic sort of record of this area, so Carthage was down there. People that were Phoenician originally, I think, and I think much of Sicily was populated by both Romans and Phoenicians, and the Etruscans were in this area. I think the Etruscans were a little farther to the north, however. So you can see on here where Rome is located. That's in the knee area of Italy there. The islands of Corsica belongs to France, and Sardinia down here belongs to Italy, and Sicily, of course, belongs to Italy as well. And then there's these other islands down here. So Pantelleria is the one that's in between Tunisia, that little peninsula that sticks off from Tunisia there, and Sicily there. So that is part of a Sicilian province there, and so that's Pantelleria. And then down here at the bottom, down here, that's Malta. And so maybe you watched Indiana Jones movies before, and you would have seen reports of the Knights of Malta protecting the Holy Grail and things like that, right? So, but these are places that they're just steeped in history, and Sicily itself is steeped in history. The part that's interesting about this today is that there's subduction going on, both in that plate underneath of that volcano that you see in Sicily there. So that is Mount Etna. So Mount Etna is erupting. Even today, I think it's erupting. And so if you probably can go to a website that's going to show you the eruption. I think recently on YouTube, there was a guy who was photographed skiing down that. So, well, it's snow-capped, right? In the wintertime, it's snow-capped anyway. He was skiing down Mount Etna. So it was kind of cool there. You can see the Tyrrhenian Sea in here. So that's that little triangle area there that you can see that is in between Sardinia and Corsica, the main peninsula of Italy there, with the mountain chains. What are the name escapes me. I'm getting old, I guess, these days. And Sicily here, right at the bottom down here, and so the African plate, trapped between the African plate, the peninsula of Italy there, and then also Sardinia and Corsica there. The Apennines. It's the Apennines, the Apennine mountain chain that runs down the length of of Italy there. So that is Italy, and so it's all related to, plate tectonic sort of things. Believe it or not, this thing is full of ocean water. You've already seen that it's a very saline sea today. It's not as saline as it used to be in the ancient past. During Miocene time, the Mediterranean Sea actually dried out. The Straits of Gibraltar closed off during a sea level fall, and in fact, I don't know if it was partially tectonic perhaps, but eventually the water made its way back in. But when it became dry, this entire ocean basin was exposed and became a lot like the Sahara. And so it evaporated all of the water out of the Mediterranean. And there were elephants that migrated onto some of the islands in here, and the whole thing dried out. And there was a whole bunch of salt that was deposited in this area. In fact, that event is called the Messinian Salt Crisis. And so the Messinian Salt Crisis happened during the Miocene. And it left behind huge salt deposits in this area. Really kind of a fascinating story. The geologic history is almost as fascinating as the historical perspective on this. And so, the Mediterranean Sea is spectacular. Is New Zealand. Now, I just got back from New Zealand, so this is kind of fresh on my mind here. Now, that's not my photograph. That was from Wikipedia there, but that is the Alpine Fault. Now, I know that these are not called the Alpine mountains that you're familiar with, because those are the ones that stretch between Switzerland and Italy and partially into France there. But in fact, these are the Southern Alps, they call these. And so that's on the South Island of New Zealand here. And you can see the trace of the fault running across that landscape. You see that gouge that sort of runs through there. It's a very active fault zone. And if you're not familiar with it, just recently here, within the last 5 years or so here, maybe 6 years, 8 years now, there was a earthquake at Christchurch. So you see the little Banks Peninsula that sticks off on the east side of the South Island here, just below the D in New Zealand there. That is where Christchurch is located, and that earthquake pretty much leveled much of Christchurch. Well, it's recovered since then, but we didn't make it to Christchurch this last time that we visited here. But I've been to Christchurch before, and it's a spectacular city, a great place to visit. Beaches, food, wonderful people, things like that. But that's where you fly out of to go to Antarctica if you're part of the United States Antarctic program. And so the folks who are part of that polar programs, you can fly out of there from a base, an American base that's in Christchurch. So you can fly to Ross Island and land at the base on Ross Island there. So that is the North Island up above the South Island here, and you can see Wellington is the capital of New Zealand. That's at the southern tip of the North Island there. And the North Island has some different tectonics going on there. If the South Island, in fact, is due to a transform plate boundary, it's a right lateral strike slip transform boundary there. So the left-hand side of the South Island is moving up to the northeast, and the southern side of the South Island is moving to the southwest there. It's a lot like California. One side is slipping past the other, and that's the Alpine Fault. And so the trace of the Alpine Fault's what you see in that photo here above it there. In the North Island, in fact, they have subduction going on, and that's a convergent plate boundary there, not a transform plate boundary. And there you get part of the Pacific plate being subducted below that North Island there. Now, the North Island used to be part of what they used to call the Australo-Indian Plate, I think it was. Today, they recognize this whole area as being a microcontinent, and they call it Zealandia. And so Zealandia would be off to the northwest on in this sort of image here. Some of that shallower water area there would be part of that. So like the Challenger Plateau there, that's over to the west of the North Island there. So these are a whole bunch of volcanoes and geysers that you get in the North Island of New Zealand. It's pretty spectacular. So when you get there, I've got some photos. I'm going to have to turn this into a slideshow kind of, but that's okay. I enjoy showing these things, and I think people kind of enjoy it. Hopefully I'm sparking your interest in wanting to travel around the world. So that is New Zealand from a map view. Here it is up close and personal. That's the West Head. That's when you get on the northern tip of the South Island and want to head to the North Island, you can take your rental car, get on a ferry there, and it'll take you and drop you off at Wellington. And so from there on, you can drive on. So you can rent a car from the southern tip, which is what we did. We went all the way down to the southern tip of the South Island and landed at Invercargill. At Invercargill, you can drive from there to see things like these Jurassic kauri logs down here, which are preserved. In Jurassic is roughly the time of dinosaurs, right? So that would have been a forest at the time of dinosaurs. The trees fell down. They're in a conglomerate. They get replaced by silica. You can see a piece of that kauri wood over here in the middle bottom here. So that's petrified wood right there. That's from that foresty area right in there. And so those are logs actually on the seashore there. So the oceans have come in and eroded much of that beach landscape, and the conglomerate's been worn away there, and it left the petrified wood behind. Those are living kauri trees over here on the right-hand side. Now they are still ancient, but they're not Jurassic in age. They're 800 years old, though, so that, it doesn't even get close to the Pleistocene, right? But even so, that they are actually absolutely ancient trees. They are a real treasure for what you see in nature in New Zealand. I love nature, and it's just a wonder to get to experience things like this. So there's a forest walk. They're very careful and very protective of their landscapes. One of the most forward-thinking countries, I would say, on the face of the earth. They're very environmentally focused, and most of the people here are very congenial, and they also they want you to do things like take a shoe wash essentially before you go visit this forest, because you can actually transport some fungus that's killing the kauri trees in many areas. Now, this is in the Coromandel Peninsula where those living trees are right there. And so you actually have a kind of like a pump, and you push this thing and it washes your shoes with a little bit of bleach water to kill any sort of fungus or anything like that that you may be carrying in on your shoes, your hiking boots or whatever. So that is the kauri forest, the ancient kauri forest, some of the petrified wood, the modern living forest there, and then you got the North Island over here as you head out of the Cook Strait there. So the Cook Strait ferries takes you right back by here. We were on the Blue Bridge ferries that went across Cook Strait here. So the next photo here shows you some of what you see, some more of what you see. Actually, these are all from the South Island as well. We went to Milford Sound to see those fjords there, and Kias are the type of wild parrots that have come up. They're absolutely fearless of human beings. It's interesting, the stories that you get out of Kias. Kias will actually attack your tires. Well, they attack the valve covers of your tires. They love things that are rubber, and they'll chew at the rubber. And so even your let me say it properly here, your windscreen wiper blades are made out of rubber, and they will attack your wipers as well. And so, people try to scare them off and all sorts of things. You can see that this bird's been in trouble before, likely. He's got some bands on him here. But he landed on our car here as we were leaving Milford Sound. You have to drive through a tunnel. So we stopped right in the road, and you can walk around. These things will be sitting there on your car looking at you. It's like, why don't you give me some food, man? It's like, well, you don't want to feed them either, right? You want them to eat natural foods. Otherwise, in the long run, you're going to be killing Kias, and that's not a good thing to do in New Zealand. We did get to see some penguins. Also, we saw the yellow-eyed penguins that you see here. That's at Curio Bay, which is right where those logs were. So the logs, in amongst those ancient logs, are some living, modern, nesting yellow-eyed penguins there. On the north end of the island, they have blue penguins. And so New Zealand, the South Island of New Zealand, has some penguins. That's from the Abel Tasman Park at the north end of the South Island. We went as far south as you could go. And that place is called Slope Point. And so Slope Point you're actually closer to the South Pole than you are to the equator when you're there. That's just a sign there from Slope Point. Slope Point's actually just behind that sign. You can actually see where the water's very shallow out there. There's a little peninsula rock that sticks out there. If you turn around and look the other direction from the parking lot at Slope Point, you have to walk in maybe a half mile or so to get to Slope Point there. But you'll see trees that are weather beaten like this, and so the prevailing winds here will bend these trees over like that. So these are actually relics from Gondwana. So Gondwana was one of these places where you get unusual trees. They had the southern beech forests in New Zealand, just like they had in many of the other continents that today are separate continents that would have been part of Gondwana back in the Mesozoic. So a few more things to show you here. This is from the North Island now. So if you cross the ferry over to the North Island, you will see this huge volcano, in fact. So that is a small volcano that you see on the upper left there. And that is Muanga. I'm going to work at this. Okay, so this is a Maori word, obviously, here. So Muanganamu. So that's that little volcano here in the foreground. You see all those power lines down there? They generate hydroelectric power here, and they also generate geothermal power here. And so that's a major electrical generation plant down there with the huge towers and everything around it. In the distance here, behind that little tiny volcano, is another volcano, but you can't really see it because you're looking across the entire volcano there. So that little volcano is rising up of a much larger super volcano. That is Lake Taupo in the distance there. So as it turns out, After you have many huge volcanic eruptions, I mean talking massive volcanic eruptions, something that modern humans have not experienced, you can blow out the entire top of a volcano, and that's what happened at Mount Taupo. And I don't recall the exact age of Mount Taupo when it last erupted, but it's been several thousand years. The lake is actually over here on the right-hand side too, and you can see another resurgent volcano in it over here. And then looking back, you can see some volcanic rim that surrounds it out there. So this super volcano is about 15 miles across, I think, or maybe 10 miles across, but it's pretty huge. And because you're at this area that's still volcanically active, it could still go off, right? Because there is still subduction going on underneath the North Island. So you're still generating magmas, and those things still go off. And so if you aren't familiar with it, about 10, 12 years ago, there's an island off the north coast of the North Island. It's called White Island, and there was a tour that went out there to go see this active volcano, and it blew up right when they were there. And so several people were killed and burned and injured from that volcanic eruption. They're very careful about where they let people go these days because of that. So, and because of that, actually, so you see signs like this over on the lower right here, dangerous ground. This is an area that's loaded with thermal pools and geysers and things like that. Now, this is not the most famous of the thermal areas around Lake Taupo. Lake Taupo is famous for some of its beaches actually have warm water in them. You can actually dig a little pool and sit in warm water around the edge of this lake. But in fact, on the north side of Lake Taupo, there's a place called Rotorua. And Rotorua is like New Zealand's equivalent of Yellowstone. And I have to tell you, Yellowstone's the same sort of thing, almost, that you see here. Now, this one is generated by subduction, so many of these lavas, in fact, are going to be these sort of like island arc basalts. In Yellowstone, you're going to get things that are related to the hotspot volcanism there. And so I'm not quite sure if they're oibs or not. I don't think they're oibs, but they're certainly basalts that are very common in Yellowstone as well. And Yellowstone's full of a lake too, so Lake Yellowstone is there. So lakes fill up huge volcanic calderas. That's just something that happens in nature. And so New Zealand's a spectacular place to visit. Go there sometime. I've only got a couple more slides to show you here. So this is the Arctic Ocean right here. That's Greenland on the north here. You can see it's kind of in that tan color. They didn't want to show it as a stark white, I think, just to make the contrast not too contrasty, I guess. There's a spreading center, and so this is a spreading center that opened up about 30 million years ago, maybe 23 million years ago, something like that. But anyway, all of the Arctic Ocean is relatively new. That's the North American plate on the right-hand side, and the North American plate goes all the way to where you see that mid-ocean ridge run into eastern Russia right there. And so that ridge, that mountain range that's in eastern Russia right there is actually part of the North American plate. And that's the Wrangel Islands out here, these other islands that are off the coast of Russia right there. So the Wrangel Islands once belonged to the United States, and we gave it back to Russia because it was just too difficult to get out there. But interestingly enough, the Wrangel Islands have yielded a fauna of pygmy, or at least small, diminutive, woolly mammoths that were alive about 5,500 years ago. And so the woolly mammoths still lived on that island 5,500 years ago. They weren't wiped out when the rest of the mammoths were wiped out across the entire northern reaches of our globe. But anyway, it's a shame. I think a lot of people want to take that DNA and reintroduce it into elephants, do some splicing, and maybe remake the mammoths after this. I'm going to show you one more slide here that's going to show you the tectonic map for the Arctic Ocean here. And so that is the northern part of our globe here, and you can see Greenland on it. I tried to orient the last map with the same orientation as this, so Greenland's at the top up here. The last map, the orientation was rotated from that, so I rotated 180 degrees just to give you the same view. But you can see the spreading center in here, marked as EB here. Sorry, I got a little bit of hiccups right now. But anyway, this is that tectonic map, and you can see where there's subduction going on around the perimeter of this area here. So that is there's more than a few concepts out of this presentation. Okay. I'm going to go through the list. I'm going to go ahead and read them to you. Oceans are important for climate and habitat. You know that, right? Ocean salinity comes from the rivers. The continental crust is different from ocean crust, and the ocean crust is made out of basalt, as my advisor used to call it, basalt. And so the ocean crust is thin. It's only from 0 to 10 kilometers thick. It's 0 when you're at the mid-ocean ridges, but it gets thicker through time. And so that's the ocean crust. It's very, very thin. It's like having oil on the top of a pool or a puddle of water, right? It's that thin compared to the rest of the mantle and everything that's down below it. So Earth is mostly mantle, as it turns out. The mantle comprises about 75% of Earth. And the core itself, the liquid outer core and the solid inner core, that's about a quarter right there. So there's just a tiny little bit that's on this crustal material that's on the outside. So anyway, the ocean plates are part crust and part subcrustal upper mantle. So everything above the asthenosphere is part of that lithosphere. So we abbreviate that SCUM or SCUM to call it subcrustal upper mantle. And together, the subcrustal upper mantle and the crust itself are about 200 kilometers thick. And those are the plates. Those are the plates. So there's 3 types of basalts, IABs, OIBs, and then MORBs. YABs, OIBs, and MORBs. And seafloor spreading occurs at these mid-ocean ridges. You know that. Seafloor spreading is responsible for new crustal material. That material can get subducted when you get to interactions with continents or maybe even other ocean plates. And so that subduction is called type 1 subduction when you have ocean plate on ocean plate. And that occurs at ocean trenches, right? So like the Challenger Deep. Hotspots are found in the middles of these plates sometimes, not just ocean plates like the Hawaiian Islands, but you also get hotspots in places like Yellowstone. So they can happen in the middle of continents as well. And they can be very, very destructive sort of volcanoes. And so hotspots are found within plates most commonly, but not extensively, not exclusively. They can actually be in places like the E04 Triangle. That's a triple junction right there that probably has a hotspot underneath of it. Most people also think that Iceland is a hotspot, and it sits right where the mid-ocean ridge is, and so it may have been partly responsible for the breakup of Pangaea. And so that hotspot's pretty important. So they are thought to come, the hotspots that is, are thought to come from mantle plumes, which probably originated at the core mantle boundary. And then the Hawaiian Islands, the Emperor Seamounts, that's an example of a hotspot in the middle of an ocean plate. And then the trajectory has changed through time. About 43 million years ago for the Pacific plate, it went a different direction and kind of hinged right there on that Mendocino fracture zone. And then the Galapagos Islands, once again, are also thought to be a hotspot, but they didn't leave a track behind them, so it may have been a short-lived hotspot for all we know. So the Galapagos are in the eastern part of the Pacific plate there. And then the Caribbean has convergence on the east and the west, so there's subduction going on underneath Central America, leading to volcanoes in places like Nicaragua and other places in that area. And then there's also volcanoes on the opposite side where the Lesser Antilles are, like Martinique and Guadeloupe. So this is the story of the convergent margins on the Caribbean plate. If you go to the south and the north, Jamaica is actually astride that plate boundary, and it's a transform plate boundary there. And then when you go to the Venezuela side, that's also a transform boundary that runs all the way out to Trinidad. And so that's what's happening in the Caribbean. And so people are not quite sure where the Caribbean plate originated, but a lot of people think that it came from the Pacific side, not the Cocos plate. And so the Cocos plate is being subducted today underneath underneath Central America, but it could have been part of that Caribbean plate, I guess is what I'd say. So the Azores is an example of where you have both hotspot and mid-ocean ridges basalts there. And so that is in the middle of the Atlantic, belongs to Portugal. New Zealand has both a transform and a convergent plate boundary. And so you get both of those. So you get the slip on on the south end down there. I will explain once again what a transform plate boundary is when we get to geologic structures, but it is a strike-slip fault. It's a right lateral strike-slip fault. And then it's convergent on the North Island, right? So you get volcanoes and earthquakes and things like that as well. So convergence is often associated with volcanoes and earthquakes. And then the strike slip is also associated with earthquakes, but not so much the volcanoes. And then lastly, the Arctic Ocean has opened up most recently. It's the newest ocean that we have pretty much. And so those are the top factoids for this presentation. I'll be making shorter presentations in the future, but I just had a lot of slides and a lot of things to show you here. And I think it's kind of interesting. You know, plate tectonics is one of the more fascinating and engaging sort of things we can talk about in geology. It's not the nuts and bolts, however. We will get to the nuts and bolts of geology later on in the semester here. Anyway, thanks for your attention. And once again, I will see you on the flip side with the next round of lectures as I get them recorded. As I'm doing this, okay, this is like the week before classes start. And so these things take about 10 hours each to produce. And so that's what's going on here is like I'm working feverishly to get this stuff out for you so you can watch it. And this you'll get to see within the first 3 weeks of the semester. So I got a lot to get done. I don't set my own assignments for this stuff, sadly. You know, it's like, and I actually am a public affairs fellow this year, so I get to host the public affairs conference in the fall semester here. Anyway, thanks for all your attention. I will see you soon. See you on the flip side. Bye now.